Okay, so you know what a head of lettuce looks like. It's a lettuce, simple, green, crisp. But what if I told you that some of the most advanced lettuce on the planet isn't growing in a field or even in water, but inside a computer? That's right. Today, we're going to build a digital lettuce, and we're following the exact recipe scientists use to pull it off. So let's just think about this for a second. Imagine you could give a plant the perfect amount of light, the perfect amount of water, the perfect temperature for every single moment of its life. I mean, no guesswork, no bad weather, just absolute peak growth, from the second it's a seed to the moment you harvest it. That's the dream, isn't it? Well, that dream is actually becoming a reality, thanks to something called a crop model. And the best way to wrap your head around it is to think of it as a digital twin for a plant. It's a perfect virtual copy that lives inside a computer simulation, and it grows and reacts based on a super precise set of rules and data. Okay, so how in the world do you build one of these? What are the actual ingredients you need to cook up a virtual plant that acts just like the real thing? Well, it really is like a recipe, a digital blueprint for life itself. The very first part of our recipe is the timeline. You know, just like when you're baking something, timing is absolutely everything. A plant doesn't just grow, it develops on a very specific internal schedule. And here's the key. A plant's life cycle isn't measured in the kind of days you and I think about. The model uses this really cool unit called growing degree days. It's basically a way of tracking progress based on how much useful heat the plant has soaked up over time. So what exactly is a growing degree day? Honestly, the best way to picture it is like a piggy bank for warmth. For our lettuce, any heat that gets above 4 degrees Celsius, clink, gets added to the bank. And once it saves up enough of these heat coins, the plant knows, okay, it's time to move on to the next stage of my life. And get this, the model is incredibly specific about it. It knows that it takes exactly 80 of these growing degree days for a tiny seed to become a sprout. Not 79, not 81, 80. That level of precision is literally coded right into its digital DNA. All right, on to our next ingredient. Now that our plant has a schedule, it needs energy, right? It needs fuel. So this next part is all about the plant's power source, good old photosynthesis. The model basically treats photosynthesis like an engine. It takes in fuel, light, CO2, and it converts that into the energy for growth. But just like the engine in your car, it has optimal conditions. If it gets too hot or too cold, or if it doesn't have enough fuel, that engine just starts to sputter. And the model knows the exact sweet spot. The perfect temperature for our lettuce's engine, 22 degrees Celsius. That's its happy place. That number is hard-coded right into the system for peak performance. And what about fuel? You'd think more sun is always better, right? Just blast it with light. Well, the model knows that's just not true. At 1200 micromoles, the engine is at full throttle. Any more light beyond that is just wasted energy. The plant literally can't use it. Okay, so we've covered the ideal schedule and the perfect power settings, but let's be real. The world is rarely ideal. To be truly realistic, our digital twin has to know how to handle stress. It has to know how to survive the bad days. So let's put it side by side. We know the perfect day is a comfy 22 degrees. But the model also defines a very specific tipping point. The second the temperature hits 28 degrees Celsius, boom, the plant officially enters a state of heat stress. And here's the cool part. The model doesn't just slap a label on it and say, oh, it's stressed. No, it calculates the exact consequences. The moment that 28-degree line is crossed, all these other parameters for things like photosynthesis and growth sensitivity kick in, and they start reducing the plant's efficiency, slowing everything down. The digital twin, it actually feels the heat. So this is all fascinating stuff, incredibly detailed. But what's the point? Why go to all this trouble to build a plant inside a computer? Well, the answer could have huge, and I mean huge, implications for the future of how we grow our food. This is where it becomes a total game changer. With a digital twin, you can run thousands of experiments in a single afternoon. You can figure out the perfect growth recipe to get the absolute maximum yield out of a vertical farm. You could simulate a crazy heat wave to see how our crops might survive in a changing climate. You can do all of this without planting a single real seed, which saves an unbelievable amount of time, money, and resources. It's such a powerful idea, and it leaves us with this really big question to chew on. We just walked through the recipe for a single digital lettuce, built from code and data. So, if we can perfectly simulate one plant, What's stopping us from simulating an entire farm? Or what about a whole digital ecosystem? The digital harvest, well, it feels like it's just beginning.